Hello, me, Sebastian, Mahmoud and Isaac have tackled the forums problem. A bit of backstory into the forums problem. It is hosted by the Farama Foundation under the mini-grid environment. The forums, as we can see on the image, is a 19 by 19 grid world with partial observability. It is also a sparse reward setting. The agent only receives rewards when certain conditions are met, which we will talk about soon. The doorways, as we can see in the image, as well as the agent colored in red and the goal colored in green, are all randomly generated. As I mentioned before, the agent has partial observability and is only able to perceive a 7 by 7 square. As we can note it here on the image as well, the agent has to take multiple steps if he wishes to cover the entire room. In total, the agent has 7 actions it can choose from. However, only 3 are applicable in this grid world, and the main 3 ones are left, right and forward. The last 4 ones, which is pick up, drop and toggle, are only kept here to be consistent with the other problems under the grid world environment. However, the agent is still able to choose from any of these 4 actions. So for the reward is defined as 1 minus 0.9 times the step count divided by max steps, and the reward is bounded between 1 and 0, or 0 and 1. Max steps is set to 100 by default, and this is defined under the environment's constants. The step count is the number of steps the agents took to reach the goal. And as I mentioned before, the agent only receives rewards when certain conditions are met. And the 2 conditions are if it managed to reach the goal, and the second one is if it timed out, which is when the step count exceeds the max steps. And in the case of a timeout, the reward is set to 0 due to failure.
The main challenges posed by the environment are the sparse reward as well as the partial observability. In this project, we primarily rely on Proximal Policy Optimization, or PPO. At its core, PPO alternates between sampling the environment and updating the policy using stochastic gradient ascent. The main idea in PPO is to restrict how much the new policy can deviate from the old one by applying clipping to the probability ratio between the 2 policies. This constraint effectively limits the size of the update, ensuring smoother learning and reducing the risk of policy collapse. This helps ensure stable and efficient policy updates. These characteristics make PPO quite well suited to environments like forums, where consistent and stable learning is essential to deal with sparse rewards and partial observability. To enhance exploration further, we integrate random network distillation. R&D introduces an intrinsic reward signal based on how novel a state is. This is done by initializing 2 neural networks. One is kept static and the other is trained to learn the output from the first. The prediction error is used as an intrinsic reward, representing the surprise of different encountered states. The better the prediction, the less surprising the state. This encourages the agent to explore unfamiliar or surprising areas of the environment. For comparison, we also include 3 baselines, namely DQN, A2C, and vanilla PPO, to evaluate what improvement can be made using PPO in conjunction with R&D. To optimize performance, we implemented a 2-stage hyperparameter tuning process, exploring the listed parameters: the entropy coefficient, the start R&D beta, the gamma, as well as the combined learning rate for V and pi networks. For evaluation, we utilize the mean and median reward, as well as the number of steps per episode. Given the reward, they are linearly correlated, but the number of steps still holds value due to its easy interpretability. The first stage involved a broad search comprising 81 parameter configurations, trained twice over 300,000 environment steps. Each resulting model was evaluated on 100 episodes. This was done to identify general regions of strong performance. In the second stage, a refined search was performed on the top 5 performing parameter sets, evaluated by the mean episodic reward. Each parameter configuration was trained 5 times on 1 million environment steps. The models were later evaluated on 100 episodes to yield the final hyperparametric tuning results. Finally, here's an outline of the implemented architecture. We start off with the CNN base in the left of the image. Its purpose is to extract relevant spatial features from the environment. These exist both in the RNN as well as the actor-critic architectures. The RND module in the center consists of a target and predictor network. Its output is, as previously discussed, an intrinsic reward signal representing novelty. The reward is scaled and added to the reward from the environment, which is propagated to the PPO actor-critic on the right. The actor-critic network is split into 2 separate networks: the actor and the critic, each with their own CNN base and linear layer. The PPO algorithm is utilized to generate actions and value estimates that are passed back into the environment. Together, they form the PPO+RND architecture, where the agent receives both extrinsic rewards from the environment and intrinsic rewards from R&D, thus promoting exploration.
In the result and discussion section, I'm going to begin talking about the first stage in our hyperparameter tuning process, specifically in this slide, stage 1, which consists of 5 subplots containing box plots and 1 table highlighting the average top 15 configurations sorted by their finally obtained rewards. Also, we make note of the top 5 configurations which subsequently were chosen for further analysis in stage 2 of the hyperparameter tuning process. However, before that, I do first like to elaborate on the box plots. Specifically, each subplot corresponds to one of the 5 hyperparameters Isaac mentioned. The x-axis specifies the values over which the hyperparameters were varied. Associated with it is a box plot, detailing the final mean reward spread for all models with that value. Moreover, there is a label on the very top. The label specifies how many of the 15 configurations had that specific hyperparameter value. Doing this for each hyperparameter and their values manages to yield us a broad yet detailed overview over what works and what doesn't. Specifically, we note that if you take the maximum frequency of each occurrence of the 15 configurations, we note that one would yield the configuration which is on the top of our list. As I stated earlier, we took the first configuration from our list and the subsequent 4, also highlighted in the table, to our hyperparameter optimization stage 2. Specifically, it's these ones in the top of the table. Now, in stage 2, contrary to stage 1, we now run each of the selected top 5 configurations 1,000,000 time steps each, and we actually observe different results in comparison to stage 1, where we ran all of them for 300,000 time steps. We see that those configurations, specifically 3 and 5, which had a very high learning rate, did not manage to generalize more than what they did at 300,000. At least configuration number 3 and configuration number 5 did perform slightly better. Nonetheless, we noticed that the configuration number 2 had the best mean and was the configuration which our final model was based on. In an attempt to establish the actual contribution of R&D, we actually tried to benchmark it against PPO without R&D, and as the graph to the right highlights, there is a consistent and pretty substantial differential in terms of the average reward which the models managed to obtain over the rollouts which the models trained. Specifically, this is over 1 million training steps. Now, in the graph to the left, we notice the frequency of the rewards obtained by the models throughout the rollouts. And we, as you see, also included A2C and DQN as some sort of baselines as well, but it's more supposed to serve as a hint towards that you can't just take any arbitrary algorithm and expect that it will solve the environment to a satisfactory extent. In fact, A2C and DQN in our experimentation failed drastically. Now, beyond simply just visualizing the results through the plots as just done previously, we thought that it would be meaningful to statistically summarize the results through this table. Specifically, the difference is clearly highlighted between PPO and PPO with R&D. If you look at the mean amount of time steps which the agent needed to take to get from the starting point to the goal. It's over 20 steps in the mean case, and when you look in the median case, it's even worse. It's about 40 steps in difference. And it seems like a big reason as to why that is that R&D actually explores the environment and manages to find the goal even if it's not immediately visible in the room it's in. Whilst without R&D, if it's immediately in front of it, it will often tend to find it, but in the cases where it's not, it doesn't. So we think that explains the statistics of this table. Now, beyond plots and tables, isn't it interesting to actually see the agent perform in the room with the trained model? Now, this is the baseline PPO without R&D, and you will now see how it performs. Now, what we observed was that the agent failed to explore the state space adequately. It was stuck in the first room during the whole clip. It did never try to reach for the doors. We also noticed a lag in its movement, and that's because the action space contains actions which do not meaningfully alter the state space. It did not learn not to take those actions. Compare this to PPO with R&D. We see that it's almost laser focused on reaching the doors and exploring not just the room it's in, but the other rooms in hopes of finding the reward. And it does so successfully. Now, it doesn't always succeed, but the very vast majority of times it does succeed, and it does so in a short amount of time.
So concluding, we have found that A2C and DQN do not generate any meaningful solutions. Both of them are rather quite bad at navigating the grid world effectively. And this is probably due to both the sparse rewards as well as the partial observability. The intrinsic rewards generated from the random network distillation have proven to be very valuable for the sparse reward setting of this grid world and have guided our PPO into exploring. We also believe that a more exhaustive hyperparameter tuning could have helped stabilize our results further. Thank you for listening.